Hello everybody. Today I want to take a look at using a lead acid battery, typically like what we would have in our cars, and using Ohm's law in order to do some calculations. Now this battery that I'm using today is a sealed lead acid battery that runs at 12 volts, which is just like your car battery, except for it's just a lot smaller. So its capacity is a lot less, meaning that if I were to leave my headlights on using this little battery, it would die much faster than if we were to use a regular size car battery, because this just doesn't have the capacity. It's still 12 volts, but just wouldn't last as long. Okay, so what I want to do is first take a look at Ohm's law. And if we look at it, I like to write it this way. There's many different ways to write it down. But let's just look at the symbols in here. So this is a V. Go ahead and get this under the camera a little bit better. So we have a V. The V stands for voltage. We have an I, and the I stands for current, or a lot of times I refer to it as amps or amperage. And then the R is the resistance, or ohms, or omega. But typically I will write the symbol ohms to represent resistance. So if I know two of these things in this equation right here, I can figure out the third. Okay. So let's go ahead and try the experiment and write these numbers down and use some equipment to do that. So right here I have a multimeter. You could use basically any type of multimeter. This one right here I have at home, and so I'm going to go ahead and use this one, but you're going to have different settings on it. Okay. Obviously off. This one right here is voltage AC. This is millivolts AC, and AC is typically what comes out of your outlets in your house. But when we're working with any type of a battery, anytime you store power, it's going to be DC power. So right here I have voltage DC, millivolts DC. Here's the ohm symbol for resistance. This is for diodes. This is for measuring temperature. This is for measuring amperage AC. This is for measuring capacitors. This is for measuring amperage in DC. So the main things we're going to use right here is we're going to use the voltage DC and the amperage DC for the experiment that we're doing here. So the first thing I want to do is just get the voltage of this battery. So what I'm going to do is go ahead and turn it to voltage DC. I have my leads coming off my meter. They're colored red and black. Typically your red is positive, your black is going to be negative. And it even indicates that on the battery right here. Okay, so I'm going to go ahead and put the red to red, black to black, and take a look at the meter. And you can see that I'm getting 12.714 volts. We'll just round that up a little bit, and let's just call it 12.7 volts. Okay. So I know the voltage, so I'm going to go ahead and write that down. 12.7 V. Okay. And now what I want to do is I want to take a light bulb, because this is a type of a load, which means it's just using energy off the battery. This is a typical light bulb that you'd find in the dome light of your vehicle, and I've just added some terminals to it. And I'm going to go ahead and connect this to the battery so you can see that it lights up. And with an old school light bulb like this, it doesn't matter which way you connect it. It's still going to work. Okay? But if this was an LED light, it would matter which way you put it in. One way it would work, one way it would not. So make sure you put the polarity correctly. So I'm going to go ahead and connect this up. And you can see that it is creating light. But the problem is I can't use my meter on this right now because this is completing the circuit, which just means it's coming out of the positive and making its way back to the negative. I need to be able to get my meter hooked into that circuit in order to get a reading. So what I'm going to do is I'm going to put my meter to DC amperage, which is right here, amperage DC. But the problem is the leads need to be put in the correct location. If you were to test this without putting the leads in the correct location, you wouldn't get a reading, or you could possibly blow the fuse that's in the meter. So I'm going to go ahead, I'm going to take out the positive terminal and put in to where it says 10 amps max. So that means if I pulled more than 10 amps, there's a fuse in this also, it would blow the fuse. So this experiment doesn't require that much amperage, so this should work just fine. So now what I'm going to do is disconnect. I'll go ahead and take my lead and put in the alligator clip like this. Okay, and I'll go ahead and touch the battery. And now the power or the current is going through my meter, out my meter, and then back to the negative terminal. So right now, to light this light bulb, it is taking 0.97. Let's just round that up to 0.9 amps of power. Okay, so go ahead and write that down. So my I, which is my current or my amps, equals, what was it, 0.98. Okay, so now we're going to use this formula. If we know the voltage and the amperage, then we're going to use the divide. If we knew the current and the resistance, we would multiply. So some simple math right here. I'm just going to go ahead and rewrite this. 12.7 divided by 0.98 equals, get my handy calculator out, try it out. 12.7 divided by 0.98 equals, okay, so we're getting 12.95. Okay, I'm going to round this up to 13. So this light bulb setup has a resistance of 13 ohms. Okay, now with light bulbs, if I were to actually put this on ohms right here and put my leads back the way they should be, okay, ohms is the resistance of electricity to go through it. Okay, if I were to actually test a light bulb, it would give me a false reading because the light bulb heats up when the power goes through it, and that heat changes the resistance. But we can go ahead and just see what it says. Okay, so it's pretty far off. It's saying that it's 1.1 ohms, which it was actually 13. And again, it's because the heat that's going through this really changes the resistance of that light bulb. So that would be inaccurate on a light bulb to test it that way. There are many things that we can test this way, but light bulbs are one that we cannot. Okay, so we know that when this is on, it's pulling, it's got 13 ohms worth of resistance. Okay, now what I want to show you just by doing some simple math here is that when we get our resistance closer to zero, typically like a bare wire is going to be closer to zero, or a wrench, okay, maybe that you're using to take the terminals off on your battery. A piece of metal is really close to zero in resistance, meaning it's really easy for electricity to go through it. So what I want to do is some simple math here and just show you. So if we kept the voltage the same, 12.7 volts, okay, but we didn't know what the amperage was, but we knew that, let's say our resistance was like 0.01 ohms, which is very, very close to zero. You're never going to get right down to zero, but you're going to get pretty close with like a wrench or a bare wire. So I want to see how much current that's going to pull through my battery. So since I don't know this right here, I'm going to use, I know the voltage and the resistance right here. So I'm just going to take, that's a divide symbol, so I'm going to take 12.7 divided by 0.01. 12.7 divided by 0.01 equals, okay, it's saying 1270 amps worth of current wants to be pulled through that wrench or through that wire. Okay, now this battery probably isn't capable of putting that many amps out, but a car battery can. And if you were to put that wrench across those terminals, you're basically going to pull that much amperage through there, which is a lot of energy, and you're going to get that wrench glowing red, or you're going to weld it. And this is the same exact principle that we use in welding class when we're using either the MIG welders or the arc welders or the TIG welders, is that we are short-circuiting the power, which creates a lot of current and a lot of heat, and that is enough heat actually to melt metal together. So that's why you always want to be careful not to have a short circuit in your electrical system. And that's another reason why we put fuses in line in our wiring. In case we had a high current in our circuit, it would blow the fuse and keep things from lighting on fire. So that's a look at Ohm's law. Again, if you know two of the variables in here, you can easily figure out the third just by using this simple little calculation right here. All right. that concludes our experiment for today. We'll discuss some more electrical principles next time we meet. Talk to you later.